Hi, I'm Bob Dopkin. I'm the Vice President of Engineering and CTO at Linear Technology, and I'm here to talk to you about current sources. Current sources are those things that we learned about in school that we were never able to find later. They're really useful in theoretical books, but trying to get a real one later is a really difficult task. Well, somebody will tell you that you can make a current source out of a resistor. You just take 1,000 volts, put it at the top of a 1 mega ohm resistor, and you have a 1 milliamp current source. That's a little inconvenient in most circuits today, especially low power portable circuits. Well, other places you'll see an FET used as a current source. A junction FET, you tie the gate and the source together. It looks kind of like a current source. It's got some real problems. I call it a wannabe current source because you don't know what voltage it's going to operate on down at the minimum operating voltage. The FETs as they're manufactured have a lot of variability. They don't work really well because the current will widely vary over production. You can put a resistor in the source to adjust the current, but that means each one has to be adjusted individually. The final circuit is made up of a couple of transistors and a couple of Zeners. The transistors with the Zeners form two current sources, and they drive each other. The circuit itself has a few errors due to transistor beta and beta changes with temperature, and mismatches in the Zeners and the diodes. The other thing it's got a startup resistor across it. If you've ever tried this circuit in production and you left the startup resistor out, you found out about it as soon as you went into production. So getting a real current source that you can buy hasn't been easy until now. Linear Technology has an IC that acts like a two-terminal current source. Two-terminal current sources can be fully floating, they don't need a ground. And to be a really good current source, they can't have any supply bypass caps across them. So we've designed this with some special design techniques that it will operate without any supply bypass capacitors. This is an adjustable two-terminal current source. It's an IC where you can set the current anywhere between 0.5 milliamp and 200 milliamps. The way it works is we have an internal 10 microamp current source which flows through an external R-set resistor. The voltage drop across the R-set resistor is usually about 200 millivolts because that's all you need for good accuracy. Then the voltage across the R-set resistor is impressed across the R-out resistor. And we get 200 millivolts across the R-out resistor, and that sets our output current plus 10 microamps. So it's very easy to set the operating current of the device. And the 200 millivolts is chosen to give approximately equal errors to changes in the current source and changes in the offset voltage of the internal amplifier. The device is designed not to need any bypass capacitors, unlike other integrated circuits. We can operate this fully floating with impedance in both lines, and it doesn't oscillate. So any current source that's good at DC should also have pretty reasonable AC performance as well. The current regulation at DC is about 10 ppm per volt, so it's excellent, and the TC is under 0.01% per degree. Here we look at the transient response, the turn-on response. We step the input up and we look at what the current does on the output. And we see it's got some overshoot, but by the time we're out at 20 microseconds, the current has settled down and it's fully started. So its turn-on response is actually excellent for a complicated integrated circuit. Then we'll look at the line transient response, how the device changes with a line transient. And here we have a 1 milliamp current source, and we can see that as the line changes, we have steps in our output current, but they settled back very quickly. The last graph is what the transient response looks like with a 10 milliamp current source. Again, we have some transients that settle very quickly. The only warning about that is that Sometimes these devices will be used with long lines that have inductance, have unknown capacitance, and it is possible with really long lines and stray capacitance at different spots to get some kind of ringing or oscillation on this at some current. You can isolate the lines with a resistor. Just dropping a few hundred millivolts across it will do some isolation. The other thing you can do is you can put a bypass cap from the input to the output, maybe 1,000 picofarads, not a real high value, and that makes the LT3092 look into a known impedance. It's stable with no bypass capacitors and capacitors across it. It's stable in both directions. So if you've got complex loads and you're worried about the impedance, just add a little bit of resistance in series with the device. But I really don't think anybody should have any problem with it. What can you do with current sources and how do you treat them? Current sources, if they're theoretical, you want more current, you put two current sources in parallel. You can do that directly with these devices. Here we want to get higher current from two LT3092 current sources. All we do is parallel the two devices, and our output current is the sum of each one. And another thing that this does is it spreads the heat out from one device to two devices on the PC board, so it's easier to get rid of the power dissipation. One of the things that we've done with this, it's all surface mount, so that you can use tricks on the PC board to spread the heat out. Want to run higher voltage? LT3092s can be extended for higher voltage by stacking two current sources. Here we have an LT3092 current source, and I've put a Zener diode across it. That clamps the voltage to the maximum operating voltage of the 3092. Then I put that in series with another LT3092 set at the same current, again with the Zener diode across it. The way this works is both LT3092s are set to the same current. One will be marginally higher than the other, and that will collapse down to its minimum operating voltage, about 1.5 volts. The other one will be absorbing all of the voltage as the voltage increases. As we get up toward the Zener voltage, the Zener will shunt current around the LT3092 and start bringing up the voltage on the second device. And the second device will regulate the current as we go up toward the total voltage across the two LT3092s. At the time that the Zener turns on, there'll be a small discontinuity in the currents, but it's usually less than 1% and doesn't damage the operation of the circuit. So you can series several of these to handle very high voltages, and the Zener diodes across them protect them and keep the voltage across each one under control. Since we're doing these for surface mount applications, one thing we'd like to do is take some of the power outside of the package. These devices are in SOT223 or other surface mount packages, and if you're running it at 200 milliamps and 40 volts, that's almost 8 watts. It'd be nice to decrease the power in the IC and be able to spread the power out over the PC board. We can do this by connecting a resistor from the input to the output and let that resistor shunt a portion of the current outside the LT3092. We select this resistor so that at maximum voltage, 90% of our output current goes through the resistor and only 10% goes through the LT3092. This takes the power out of the LT3092 and decreases the power dissipation by a factor of 4 over an unmodified circuit. So that if we're using this at 40 volts and 200 mils, we would be decreasing our power dissipation to 2 watts, or in this case, at 100 milliamps to 1 watt, which is easily dissipated in this PC board. And that's the basics of a two-terminal current source, the LT3092. If you have more questions or want more information, We've got data sheets and applications up on our website, www.linear.com. We have application engineers if you want to call in. And if that doesn't work, you can call me directly. Thank you.